This is Accelerating GPU Algorithms in Pure Python, and this is Bryce Lelbach, and welcome. Let's give him a long round of applause.
There we go. Sorry about that. So hi everyone, I am Bryce Lelbach, and welcome to my hometown of Manhattan. I live over about 6 or 7 blocks to the east of here. I am a principal architect at NVIDIA, where I drive our strategy for parallel programming models, compilers, and libraries. I've served in leadership roles for several programming languages and standards bodies. I chaired the US Programming Language Standards Committee for a while, and then I chaired the library evolution group of the C++ committee. Historically, I've been a C++ person. But I've recently become a convert. I've gotten involved in NVIDIA's CUDA Python efforts. And I'm glad to be here to give my first Python talk. So I started off my career with parallel programming. Like when I first started learning how to program, I was working for an HPC center, and that was the only way that I learned how to program. And I think that's been incredibly helpful to me in my career, because by default, we humans tend to think sequentially. And parallelism is often seen as challenging and complex, a tool to only be used sparingly and cautiously and only by experts. But today, we live in a parallel world. And almost every hardware platform is parallel, from the smallest embedded devices to the world's largest supercomputers. And so we have to change our mindset. Anyone who writes code must learn to think in parallel, and parallelism must become our default. And when I give talks like these, that is sort of what I'm trying to instill more than anything else, is the mindset and the philosophy behind parallelism. So this is a talk about writing speed-of-light GPU kernels in pure Python. Now, why would we want to do that? There are many excellent GPU programming libraries out there, like CuPy, PyTorch, CUDA, and we have Python APIs for almost all of the NVIDIA math libraries, like cuBLAS and cuFFT. And so you should definitely try libraries first before you go and start planning to write your own kernels. Not only will they make your life easier, but they'll often give you better performance because they're written and tuned by a team of experts. And they'll be updated as hardware and algorithms evolve over time. So they're basically going to do free work for you. But sometimes there's no library that does what you need. Or you've tested and found that you can't get the perf that you need with the libraries that do exist. And that is when you should consider writing your own GPU kernels. Now, the good news is that you can now write those GPU kernels in Python and get the exact same code and performance that you'd get writing it in CUDA C++. So the primary way to write GPU kernels in CUDA Python is with Numba's CUDA backend, which is going to be the primary technology I'll be talking about today. So Numba is a JIT compiler framework for Python that is widely used and pretty popular. I bet some of you have heard of it or used it. So it takes Python bytecode and it lowers it to Numba-IR, and then it performs type inference and some other transformations upon it. And then it takes that Numba-IR and it lowers it to a backend IR, such as LLVM-IR or NVVM-IR, which is NVIDIA's version of LLVM. And Numba supports NumPy arrays and frameworks that build on top of NumPy, like SciPy. Now, Numba has a compilation mode called NoPython, in which it will compile code in such a way that it will run without the involvement of the Python interpreter at all. So there's no reference counting or object lifetime management. Now, this has some semantic compromises. In many cases, if you're just working with arrays and scalar values, you won't be able to observe those semantic compromises. But usually this is what's recommended because it's best for performance. And if you're using Numba's CUDA backend right now today, that is the only option, is to use the NoPython mode. We don't have a Python interpreter that's running on the device. Now Numba is modular, extensible, and hackable, which is a large part of why it is successful. You can easily customize how number lowers things. For example, if you wanted a function in your code to be lowered to a certain assembly instruction, you could write an extension for that. If you wanted one of your classes to have a certain layout, you could write an extension for that. So what exactly is a GPU kernel? A GPU kernel is a function that is run by many threads at the same time. So let's go ahead and write our first one, which will just copy elements between two different arrays. So with number CUDA, we must decorate our functions with CUDA.JIT to use them as kernels. Nope, we lost audio there? Nope, doesn't do good. So the inputs to our copy kernel will be NumPy compatible arrays. A subset of the NumPy array API is supported in device code. We'll see some of that a little later. The first thing we do within the body is determine the unique index of our current thread. So this CUDA.grid function gives us a global thread index. So the thread indices start at 0. And then we copy one element from the source to the destination using our unique thread index to select which element this thread should copy. If we have 8 threads, for example, we'd copy 8 elements, like so. Now on GPUs, threads are grouped together into a hierarchy. The lowest level of that hierarchy is a warp of threads. All of the threads in a warp execute the same instruction together at the same time. Some of those threads may be inactive during the execution of a particular instruction. For example, because they're not taking a particular branch, but they aren't doing something else. They're still executing in step with that warp. Now, warps have a fixed size that is dictated by the hardware architecture. It's been 32 threads on NVIDIA hardware since at least the start of CUDA. It probably will always be 32. Now, threads in a warp can communicate with a variety of fast synchronization primitives. Now, warps are grouped together into thread blocks. All the warps in a block run at the same time, but each individual warp may be executing different code at the same time. So it may be in a different place in the program. Each warp has its own program counter. Blocks can synchronize with each other and communicate via a special kind of fast memory called shared memory, which we're going to discuss a little bit later. So we call the set of thread blocks that are executing a kernel function the grid of threads. Now, blocks and grids are shown here as one-dimensional, but they can actually be 2- or 3-dimensional, as we'll see a little bit later. To launch our kernel on this thread hierarchy, we need to provide both execution parameters and function parameters, which we do here. Execution parameters are provided via the indexing operator. The first execution parameter is the number of blocks, which is 2 in this case. The second execution parameter is the number of threads in each block, which is 4 here. So now let's write a slightly more capable copy kernel. Our previous copy kernel copied 1 item per thread. Now that's not great for performance or functionality. We're not going to saturate memory bandwidth with so few operations per thread. We also don't want the number of threads to be dictated by the input size. So we're going to write a version that copies multiple items per thread. The quantity is specified with an additional parameter here. When determining our unique thread index, we need to multiply it by the number of items to account for the extra items that all of the prior threads in the thread index ordering will have handled. And we'll have a simple for loop that will copy all of our items. When we launch our kernel, we need to calculate how many blocks to launch, and that will just be the number of items in the array, which is n here, divided by the number of thread blocks, b, times the number of items per thread, t. The second parameter is just our thread block size, which is b. Now let's think about how this kernel will actually access memory. Here's a table showing what a grid of 4 threads will access when running this kernel. So thread 0 will access items at index 0, then index 1, then index 2, etc. Now, this might look great to you, right? Like we're moving through memory contiguously without any strides. If you know anything about memory access patterns from CPUs, this is sort of what you're supposed to be doing. And so an optimizing compiler would presumably reorder the loads and stores, grouping them together, and then they can even be combined into vectorized operations. Now, all of this is true on CPUs, but this is not how GPUs work. Remember, on GPUs, all the threads in a warp will execute instructions together. So on the first step, the warp will load from index 0, 4, 8, and 12. That's not a contiguous load, that's a strided load. We'll have 4 separate loads that will have to go through the memory hierarchy. That's not good. So we have to flip our thinking here. Let's try again. This time, we're going to have each thread do strided loads and stores, such that the entire warp, and in fact the entire thread block, will load from a contiguous block of memory at the same time. So we can no longer rely on that CUDA.grid thread linearization utility. Now we'll have to access the raw components of our thread and block's coordinates and dimensions to calculate the right stride. So blockdim is the shape of our thread block. We're just working in 1D now, so blockdim.x is the number of threads in the entire thread block. And block index is the index of our thread block in the thread grid. And then thread index is the index of our thread within our thread block. It's just local, not a global index. So next, we need to determine how many items are handled by each thread block, which is just the threads per block times the items per thread. We'll call this value tile. Now we figure out the start of the chunk of items that this thread will be responsible for. And that will be the thread's index in its block, plus the number of items that all lower thread blocks will handle. Then we do a strided loop, copying elements, where our stride is the number of threads in our block. So now let's take a look at the memory access patterns that we'll get with this kernel. So now each thread in the warp will load from a contiguous set of indices. So 0, 1, 2, 3 in our example here, 4 threads. So the warp will just issue one load here, which is far more efficient, one contiguous load. So this is called memory coalescing, and it's a very important part of getting peak performance on GPUs. Now, the GPU compiler can reorder the loads and stores and combine them up to the maximum load and store size. While different warps within a thread group issue instructions independently of each other, there are also benefits to this memory pattern at the thread block level, such as improved cache behavior and ultimately less traffic to global memory. So in our first naive example, we had what is called a blocked arrangement of the aggregate tile of items that each thread block handles. So each thread was responsible for a contiguous set of items in the global input and output. But in our second example, we had a striped arrangement, which is often more efficient. And in the striped arrangement, the aggregate tile is partitioned across the thread block with a stride of the thread block size. So now let's talk a little bit about the different types of GPU memory. There's 3 different types of memory primarily that we think about that GPU threads can utilize. And it's important for us to understand the trade-offs between them before we move on. So local memory or register memory is the memory that is private to each thread. So this is often called stack memory on CPUs. This memory is used both implicitly for local variables and can also be explicitly allocated in the CUDA Python programming model. It is incredibly fast to access as it is physically located within the GPU processor port. However, something that's in one thread's local memory cannot be accessed by another thread. Now, if we want to have fast communication between threads, we need to use shared memory. Shared memory is storage that can be accessed by all the threads within a block. It must be explicitly allocated. Shared memory is used to implement block-wide communication protocols. which is what most algorithms, parallel algorithms, break down to, is some form of communication. So like local memory, shared memory is very fast to access, although it is banked. Finally, we have global memory, also known as the heap. Global memory has hardware caching, so there's an L1, an L2, etc. And unlike local and shared memory. And that's good because accessing global memory is very, very, very slow. Not just for GPUs, but for CPUs as well. However, with CPUs, they are typically out-of-order processors, and they typically have a lot lower per-thread latencies. So they experience less of the slowness of accessing global memory than GPUs do. Now, GPUs are largely in-order processors, and they have higher latencies. And so we have to suffer the full latency, the full slowness of memory loads and stores. We must either hide that latency by batching operations, doing something else while the memory load is coming in, or by avoiding it, by minimizing global memory traffic. So now let's take our copy example one step further. Instead of writing all of that low-level I/O and indexing ourselves, we can use a library. CUB is a CUDA C++ library of kernel authoring tools. It has a number of cooperative communication primitives, such as loads, stores, reductions, scans, sorts, etc. And there are versions of these facilities for all levels of the thread hierarchy, from within a single thread, to within a warp, to a thread block, to even something like a global reduction across the entire thread grid. Now, CUB has been the gold standard and speed-of-light solution for kernel authors for many years, and it is widely used to implement many of the libraries that you may be familiar with. And now you can use CUB when writing CUDA kernels in Python. CUB's primitives are available in the CUDA.cooperative module that we've recently put out in beta. And we're working on improving it and adding more and more features to it. So let's use CUB in our final version of this copy kernel. First, we're going to set up our imports. So we need NumPy, we need NumFOCUS, and then we need the CUDA cooperative module. So now we'll set up our grid configuration. So N will be the size of the input and output. B will be the number of threads in each block. And then T will be the number of items that each thread will load into local registers and then store out to global memory in one batch. To use CUDA cooperative algorithms, you'll need to instantiate an algorithm object outside of your kernel. Now, this is necessary because we have to pre-compile the underlying CUDA C++ code, and that needs to happen in a host code before you launch. So the block-wide load and store algorithms take 4 different parameters at configuration time. There's the data type, the number of threads per block, the number of items that each thread works with at one time, and which block-wide I/O algorithm or strategy to use. The direct strategy loads data in the blocked arrangement that we discussed earlier. Now, the striped strategy that we're using here will load data in the striped arrangement that will give us memory coalescing. There's also a transpose algorithm that we're going to use later, which loads data in the striped arrangement, but then will locally exchange the data with other threads in the block so that you end up with a blocked arrangement in the local memory. For right now, we're just going to use striped. CUDA.cooperative algorithms utilize that fast block-wide shared memory that we just discussed. Now, we need to calculate how much shared memory will be used by our algorithms. We also need to collect the set of binary objects that we need to link against. And right now, today, you can do that with this little glue utility function that will take a bunch of these algorithm objects and return to you the temporary storage requirements and the set of binary objects that must be linked against. Now, we have to pass that set of binary objects as the link parameter to the CUDA.jit decorator. Now, hopefully in the future, this linking is going to be done automatically. That's something that we think can be done down the road. Now, within the kernel, we need to allocate the shared memory for the algorithm. which we do with the CUDA.shared.array function, which is going to return us a NumPy-like array. Next, we need to allocate the local memory, the registers, to store the batch of items that we'll load. In our prior examples, we just loaded and stored from global memory without any locals. This is actually more efficient as it allows us to overlap global memory latencies. Then we'll calculate the base index of the items that we're responsible for, just as we did in the prior example. Maybe a little bit cleaner here. And then now we can do our block-wide load. So we pass this primitive to the temporary storage, the chunk of global memory that we'll be loading from, and the local memory that we'll be loading to. And both of those parameters are arrays. And then every thread in the block is going to participate in this operation. They're all going to execute this load operation at the same time and then collaboratively communicate with each other to load in the data and to do the exchanges that might be necessary if we were using an I/O algorithm that required something like a transpose, as we just discussed. And then we're going to do our global store, passing it the temporary storage, the chunk of global memory that we're going to write into, and our local items. Now, in between those two block-wide operations, we need to synchronize all the threads in the block because the shared memory will be used by both the load and the store, and we don't want a data race. So sync threads is a synchronization primitive that will synchronize all the threads within the block and then will ensure memory ordering between them. So after the sync threads, we can then safely reuse this shared storage. And finally, we set up our inputs, outputs, and launch our kernel just as we did before. And that's it. We've got an efficient, scalable copy CUDA kernel written in pure Python. And this would be JIT compiled to the same code that you would get if you wrote this in CUDA C++. Now, don't actually write this. You should use CUDA memcopy because we have a library that will do it faster. But this is just for demonstration purposes. All right, let's look at another example, which will be matrix transposition. So transposing a matrix flips it on its diagonal, switching the row and column indices of all of the elements. So for example, the value at 3, 1 here is going to be exchanged with the value at 1, 3. Now, using a row major layout, also known as C-style, our matrix will have this representation in physical memory. So all of the elements in a row will be stored contiguously in memory. So let's look at the code. First, the problem and the grid configuration. So our input and output will have a 2D shape. This example that we're writing will support rectangular matrices too. The best strategy for an efficient transpose on a GPU is to split the input into 2D chunks, each of which will be handled by a different thread block, as we're showing here. Now, tile will be the dimensions of our square chunks of the input. Next, we determine the size of our thread grid by calculating how many thread blocks we'll need to handle all of the tiles. We'll come back to the kernel in a minute, but let's look at how we launch it first. So first, we're going to create our input and our output, and we're going to pass them as flattened arrays into the kernel so that we can do some indexing tricks. In our prior examples, we just used NumPy arrays and passed them directly to our kernel. Now that works and is fine. Under the hood, what it will do, it will copy the inputs to the GPU before the kernel launch and then copy them back afterwards. However, that will force the kernel to launch to be synchronous, and it will also implicitly perform an expensive operation, data transfer, and it'll actually do it twice implicitly because it'll do a transfer to and then a transfer from. It's often better to manage this explicitly, especially if you're launching multiple kernels where you might not want something to come back to the CPU in between two launches. Now, NumFOCUS has a special device array type for this purpose and facilities for converting NumPy compatible arrays to device arrays and transferring between host and device, which we are using here. Now let's move on to the kernel itself. So first, we must set up the cooperative primitives that we'll use just as we did before. We need a block-wide load and store, just like before. Remember, the parameters for these are a data type, the number of threads per block, the number of locals per thread, and the algorithm. And this time, we'll need striped loads and stores, or we'll need, strided loads and stores, and we'll see why in a moment. Our chunks of data are tile times tile large. We're going to have tile threads in each block and tile locals per thread, giving us the desired size per thread block. And we're going to use the striped algorithm just as we did before. So we need an additional primitive, a block-wide exchange that we'll use to do the local transpose of each tile. So finally, we determine the temporary storage requirements and binary objects. So now let's take a look at the body of the kernel itself. First, we're going to allocate shared memory for communication and a tile of local items, just as we did before. There's nothing new or exciting here. Then we're going to manually calculate the base of the tile in the global input using a row major layout. Note that we use both blockindex.x and blockindex.y here because we have a 2D grid of thread blocks, although the thread blocks themselves are 1D. Then we do our striped and strided load from the global input into our local memory. Our stride for memory will be the number of rows. And finally, we do a sync threads after the load so we can reuse the shared memory in the next operation. So let's look at what we're actually doing here. For each block, our strided load gathers tile number of partial rows from the input. This strided memory access pattern is maybe suboptimal. Why not just load the higher rows, which would be contiguous? Well, we want to maximize memory reuse and caching by performing local transposes of the tiles in each thread block. And to do that, we need chunks of items that are logically next to each other. So now that we've loaded the items, we need to do the local transpose, which will look like this. Now let's see what it's going to look like in the code. So we're going to use that striped to block exchange to do this. So this will take block-wide data in a striped arrangement and transform it to a blocked arrangement, which will affect the local transpose that we're after here. Now next, we need to write the locally transposed items to the output. Now the whole chunk itself needs to be written back to a transposed chunk in the output as shown here. So there's actually two different transposes that are happening. There's a transpose locally within the thread block, and then there's a transpose of the entire thread block went back into the global matrix. So in the case of block 1, 0, we need to write to the indices that block 0, 1 read from. And that will give us this. And then at the same time, block 0, 1 will be writing to the indices in the output that block 1, 0 read from, which will ultimately give us this. And the same thing will happen for the other two thread blocks not shown here. To transpose the store to the output, we need to switch from row major indexing to column major indexing when we do the store. And so we compute a new base in column major here. And then finally, we do our strided store, this time with a stride of the number of columns. And with that, we are done. We've got a speed of light matrix transpose CUDA kernel written in pure Python and small enough to mostly fit on one slide. And this will perform as well as writing the equivalent CUDA C++ version of this code. So now we're going to move on quickly to one more example, which is a softmax kernel. So the normalized exponential function softmax takes a vector of numbers and normalizes them to a probability distribution. So put more simply, it takes a 1D array of numbers and converts the values such that each number is between 0 and 1, and that the sum of all those adds up to 1. So this is commonly used in machine learning, for example, as one of the final layers in our classifier or in reinforcement learning for action selection. So today, we're going to look at how to compute softmax of many vectors at once in parallel. So to compute the softmax, you take the natural exponential of each element of the input and then divide that by the sum of the natural exponentials of all elements of the input. For numerical stability, we derive a slightly different formulation to avoid summing numbers of drastically different orders of magnitude, and the formulation is there. So this is the formula that we need to work with. Now we have to do two operations that require communications between threads here. First, we need to determine the max, and then we need to sum the exponentials up. And both of these are just reductions. So we're going to partition our input into rows, each of which will be handled entirely by a single thread block. So let's start with our problem and grid setup. We'll have a 2D input and output, and we'll parameterize how many items each thread has in local memory, which will allow us to control register usage and batching. The number of threads in each block will be dictated by the input shape and the number of items in each thread. A more advanced version of this kernel and the transpose kernel would use additional iterations within the kernel to allow us to set the amount of locals per thread independent of the input size, and to keep the locals per thread and threads per block completely independent of the input size, so it can work with any arbitrary input size. That's a little bit more complicated. There's an example of that in my repo with all of these little examples if you're interested. So next, we need to create our cooperative primitives, just as we've done in these other examples. So once again, we need a block-wide load and store. But this time, we're using a different I/O algorithm, warp transpose, which loads data striped for memory coalescing, and then locally transposes it to blocked. And we're doing that here to ensure that within each thread, these sums are performed in the original order of the input, which improves numerical stability. So next, we need a max reduction. And we'll create one by instantiating all reduce with np.fmax as the reduction operator. And we'll also need a sum reduction, and we'll pass np.add as the operator for this one. And then that's it for the configuration. And then this time, we're going to look at what the launch looks like. This time, we're going to pass 2D arrays into the kernel. In the transpose example, we passed 1D arrays, and we create those 2D arrays right here. But the grid shape will be 1D, one thread block for each row. Now let's look at the kernel R cell itself. So we allocate shared and local memory, just as we've done in all of the prior examples. Nothing new here. And then we load the entire row into memory. As we just discussed, this will be a striped load that will then be transposed to blocked locally. And then next, we find the maximum in each row by calling that all-max algorithm. And then we compute the exponent of each item minus the maximum item. And then we sum up all of those exponents with another reduction. And then we divide each of those items by that sum. And then finally, we store the entire row to the output. And that's it, we're done. We've got a nice short little softmax kernel. This is very similar to the style of softmax kernel that's in LLM.C, and it'll give you roughly that performance. It'll lower down to code that's very similar to what that would be. So a couple takeaways. First of all, leverage libraries whenever you can, even when you're writing kernels. This code would not be anywhere near as short or as clean if I wasn't using CUDA cooperative library. And you can, today, now, write speed-of-light GPU kernels in Python. We're working on making that even easier and more full-featured. It's also important to think carefully about memory layout and access patterns. All right, with that, thank you for your time. I think if you have questions, you can come find me afterwards because I've got to give up the room. Thank you all.